All right, welcome everyone to the beginning of our study of radicals and square roots and cube roots and things of that nature. Today we're going to be looking at just basic roots. What are they? And some radical expressions and how to simplify them with variables. All right, so let's go ahead and begin. We are really getting out of the square root. We're very familiar with the square root, and what we want to do is we want to extend that idea into the higher roots. Now, the first thing that we are going to look at is really just the pattern of what's going on here. We know that 5 squared is 25, and that means that 5 is the square root of 25. All right, that's the thing that we know about square roots, but we can extend that to say if we know that 5 cubed is 125, that means 5 is the cube root of 125. And we can continue this for 5 to the 4th power is 625. That means 5 is the 4th root of 625. We can continue that to the 5th root. We could go on to the 6th root if we wanted to, but eventually those numbers get very large. And what we really want to just say is if a number a to the nth power is equal to b, that means a is the nth root of b. So we have 5 as the 5th root of 3125, 5 is the 4th root of 625, and so on and so forth. And this could be for any number. All right, a couple things that we need to make sure we understand. First is that you cannot take an even root of a negative number, something along the lines of square root of -9. That doesn't exist because we know that we cannot take the square root of a negative number. But it goes on to the other even roots, like the 4th root. We cannot take the 4th root of a -81 because it's a negative number and it's an even root. So that answer doesn't exist. With the even roots, as we've known in the past, when we are taking the square root of 25, technically we have two answers, both positive 5 and -5. And the last little piece of information we need to know is we can take the odd root of a negative number. So we could actually, in this case right here, take the cube root of -125 because -5 to the 3rd power is -125. All right, so that's really our definition for the nth root. Let's take a look at what that's going to look like in a real example. We want to find the cube root of these 3 numbers. So if I wanted to find the cube root, what we want to do is we want to look at it as a actual, what does the symbol look like? That right there is the cube root. We call this the square root, and the number in front, called the index, is a 2, but we don't write it. We understand this to be the square root. If there is a 3 in the front, that means it's the cube root. And we're looking at 0.008. What I want to do is I want to think about this as a fraction first. And I know that 0.008 is 8 over 1,000 because that is the 1,000ths place. And in any radical problem, we take the radical of the numerator and the radical of the denominator separately. So we're asking ourselves, what number to the 3rd power is equal to 8? Well, we know that to be 2. We know 2 to the 3rd power is 8, and therefore the cube root of 8 is 2. Likewise, we want to know what to the 3rd power is equal to 1,000. And since there are 3 zeros behind there, the cube root of 1,000 is 10. So we get 0.2. Well, if I want to take the cube root of -1,000, Because the question is negative, the answer is negative because the cube root of a negative number is negative. And we just figured out that 10 to the third power is 1,000. So therefore, the cube root of negative 1,000 is negative 10. And the last one here is a fraction. And so again, we're looking for what number to the third power is 1, and we're looking for what number to the third power is 27. Well, the cube root of 1, or really what to the third power is 1, and 3 to the third power is 27, so that means the cube root of 27 is 3, because we know this to be 3 cubed to be 27. And there we have our first three answers of our examples. So the cube root of 0.008 was 0.2, the cube root of a negative 1,000 was negative 10, and the cube root of 1 over 27 is 1/3. So let's look at an even root. If we had a fourth root, so again, the index is going to be a 4 on our root. We know the fourth root of 1 is 1, but it's also negative 1. So we know that the fourth root of 1 is both 1 and negative 1. If we were to take the fourth root of negative 0.001, if we remember, the last page says we're not allowed to take the even root of a negative number, so this does not exist. So DNE means does not exist, and that's really all you have to write for that one. There's no answer to this question. And the last one is another fraction because we're looking at fractions, decimals, and whole numbers, and we look at 16 over 81. We want to know what number to the fourth power is equal to 16. And since 16 is a small number, this probably has to be a small number as well. And it's going to be 2. 2 to the fourth power is 16, and therefore the fourth root of 16 is 2. And then what number to the fourth power is equal to 81? You can do a little bit of work and figure out that this is a 3. 3 to the power of 4 is 81. And since that's the positive answer, we also get the negative answer of negative 2/3. All right, so that's looking at the numerical values. Let's move on to the algebra piece and looking at some variables. If you are given something along the lines of this, we were to take the square root of x to the third. Now we can do this. This is algebra. We understand that we are allowed to do all types of algebra, all types of math with variables. So radicals are no different. What we're going to be looking for are multiples of the index inside the exponent. All right, so we look at this. We have the index is a 2 because it's square root. So what we're essentially going to do is we're going to say that this is, what are the multiples of 2 that are less than 3? In this case, it's only x squared times x, because we know x squared times x is x to the third power. And then we can simplify from there. We know that the square root of something squared, so the square root of 9 is the same thing as the square root of 3 squared, and we get 3. Well, that works the same way with variables. The square root of x squared is just x. with a square root of x left over on the inside. So let's take a look at a few more challenging examples. We're going to look at a few good examples. The first being, let's look at the square root of 36 x to the fourth times y cubed. So because we're looking at the square root, we're looking for squares. So to use the numbers here, we know that 36 is a square. It's the square of 6. So we're going to write that as 6 squared. X to the fourth can be written as x squared squared. Remember, we're looking for a square. It just so happens that this is x squared squared. When you have an exponent to an exponent, you're going to multiply the exponents together. Then we have a y squared and a y, just as we did in the previous example. And then we can simplify from there. When we say the square root of 6 squared, that gets a 6. The square root of this thing squared is that thing, so it's x squared. The square root of y squared is y, and the square root of y has to remain. Once you get the hang of this particular type of problem, you'll be able to find shortcuts that make your life a lot faster in this particular type of problem. What if we had 72 times x to the fifth? So again, we're looking for square numbers inside of these two numbers themselves. 72 is 6 squared times 2. 72 is 36 times 2. I'm going to write that as 6 squared, though. And if we were to write x to the fifth as some power of 2, I could write it as x to the fourth times x. And as we noticed in the last example about x to the fourth, we're going to do a little trick here. The square root of 6 squared is going to be 6. The 2 is not a square, so it stays inside the radical. And the x by itself is not a square, so it stays inside the radical. Now, because this is the square root of x to the fourth, this becomes x squared as it did in the last example. All right, we have to do a few of these, a couple more of these examples here just to try to get us in the kind of the quicker mode of doing these problems. What about the cube root of 16 x to the fifth y to the sixth? All right, so we need to know about 16, and we need to know if there's a cube root or a cubic number inside of 16. Something to the power of 3 equals to 16. Well, we know that 16 is 8 times 2, and it just so happens that 8 is 2 to the power of 3. So we're going to write this as 2 to the power of 3 times 2. And then we need to look for multiples of 3 inside these variables. Well, I can write x to the fifth as x cubed times x squared, because 3 is a multiple of 3. And y to the 6th is a multiple of 3. So we're going to use that idea as a multiple of 3. All right, so cube root of 2 to the 3rd power, that's going to be 2. And then we have a cube root left over because not everything gets to come out of here. So the 2 to the 3rd power becomes a 2 on the outside. That 2 that's not a cube has to remain. The cube root of x to the 3rd is just x. But the x squared is not a cubed, so it has to remain. And then the cube root of y to the 6th power. I want to take a look at this. If we looked at the cube root of y to the 6th, I want to show a little trick here. This becomes the cube root of y cubed squared, which means the cube root, oops, sorry, I wrote those backwards, squared to the cube, to the 3rd. Because the cube roots and the cube cancel, this becomes y to the 2nd. And you notice that 6 divided by 3 is 2. So this becomes y squared. That would be our final answer for this particular problem. Let's look at one last one, trying to use a really good trick here that works for the variables. So knowing the numbers pieces, trying to simplify the radical of a number, that's looking at powers of numbers inside of that number, just like we did with the 36, the 672, and that 16. But let's look at x to the 3rd, y to the 5th, and z to the 4th. And let's look at the square root of this number. I want to think about this as a trick, looking at dividing. So because the index is a 2, if I was to divide 3 by 2, I would get a 1 with 1 remaining. So there was like an x, this is essentially what I'm doing here. This is x squared and x. So the square root of x squared became x to the 1st, which I don't need to write 1. And then there was 1 left over inside the radical. In the same way, this is y to the 4th times y. So if I was to take 5 divided by 2, I would say that there was 2 with 1 remaining. And then if I was to take 4 divided by 2, I would get 2 with nothing remaining. And that would be our final answer. And this works for every root. So if we were to do the same thing with the cube root of x to the 4th, y to the 5th, and z to the 3rd. 4 divided by 3 is 1 with 1 remaining. 5 divided by 3 is 1, so y to the 1st, with 2 remaining. And 3 divided by 3 is 1 with nothing remaining, and that is our final answer. So that is a faster way to do the variables, thinking about division, because it's really just breaking it into groups of the same power. All right, so let's look forward at what is next. Next is just a helpful set of numbers. It's really good to have certain numbers just off the top of your head. Most of you should probably know what your square numbers are. 2 to the 2nd power is 4, 3 squared is 9, 4 squared is 16, that kind of idea. Some of you might even know some of your cube numbers. 2 to the 3rd is 8, 3 cubed is 27. 4 cubed is 64. So cubes are a very good set of numbers to know. I gave the first 5 to fourth powers and the first 4 fifth powers just because those numbers get so large, they're not always used, especially in a textbook like ours. But I did give the powers of 10. Notice that if you square 10, you get a 1 with 2 zeros. If you cube 10, you get 1 with 3 zeros. That pattern continues forever. If you did 10 to the 7th power, that would be a 1 with 7 zeros. All right, so that's going to finish us off here. Those of you that like to get ahead, I have put an assignment on the end here for our textbook. So this is page 366, and this is going to be 1 through 53 odd. And we're going to be, I just want you guys to get a head start here just because you guys don't have your assignment sheet yet. All right, I will see you guys in class.